Hello. In previous video, we have discussed how to perform DC analysis and nested DC analysis. We have plotted ID versus VDS and ID versus VGS. In this video also, we'll be doing a bit similar, like we'll be plotting ID versus VDS and ID versus VGS, but we'll add on some new things like by varying WL and threshold voltage and lambda, parameters of the MOSFET and model parameters. So we'll see the syntax of how to vary parameters and model parameters. So here I have wrote the set of code which contains the voltage sources and more devices which are connected like this. So now we will write control block which we want to perform. So I'll perform ID versus BDS for different W first. So here I have done nested DC analysis as shown. So I'll vary W and I'll plot the things. So I'll write the control block dot control. So it's a similar like for loop in C program. So I'll write for each variable. So this is the syntax of for loop in Ngspice. We need to write for each variable. We can give variable name what you think. So for each variable, I want to choose variable as 25 nanometer, 250 nanometer, and 2500 nanometer. So these are the values of the variable. And what I want to do is I want to alter width of the MOSFET. So I'll write syntax as alter M1. So we want to vary the parameters of M1. So we'll write as alter M1. What I want to vary? W. So W is equal to dollar variable. So what I am telling Ngspice in this line is alter M1. I want to alter M1 W equal to dollar variable. So after this, I want to run this loop. And while running the loop, what I want to do is I want to plot the things like ID versus VDS. So plot minus I of VDS versus voltage at drain. So what I want to give title as W dollar variable. This will be shown on the diagram. So here I wrote the for loop like for each variable. I have defined the variable values. And what I want to do is I want to alter the width of the MOSFET, which I have written here like alter M1. What I want to vary, that should be written here. Like I want to vary W, so I have written W. When I want to alter length of the MOSFET, I'll be writing L here. And after writing the for loop, I have to run the block. So I'm using run command. And after that, in for loop only, I want to plot the things. So I have used plot command. And after completing this, I want to end the for loop. So I'll be using end. After ending this for loop, I want to end the control block. So I'll be using dot .nc to end the control block. And after writing entire program, I want to end the netlist. So I'll use .n command. Yeah, all right, it's done. I'll save and I'll run. Yeah, here we can see for different W we got the things. Yeah, here for 25 nanometer, and here it is for 250 nanometer, and here it's for 2500 nanometer. Here for 25 nanometer, it's in the range of nano amperes, and here for 250 nanometer, it's in the range of microampere, and for 2500 nanometer, it's in the range of milliampere. So clearly we can see that as width increases, current increases, we know that. So as the W increases, ID is increasing. So We are done with varying W. So now we want to vary the length of the MOSFET. Similarly, we'll go and do the changes in the netlist. So here I want to, for user friendly, I'll write here varying L, and here it remains the same, the DC analysis. And here instead of W, I can write as L. So here we are telling alter M1. L is equal to dollar variable means I want to alter length of the MOSFET as what we have defined for variable like 25 nanometer, 250 nanometer and so on. And in title what I want to label as L dollar variable. Yeah, if we run this we see as width increases ID should decrease. Yeah, yeah, fine. For 25 nanometer, we say in the range of milliampere. Here it's 45 milliampere highest current we may see. And here it's in the range of milliampere only, but 3.5 as length increases, current ID should decrease. Yeah, we have satisfied. And here it's in the range of microamperes. Yeah, we are done. So now our next step is instead of varying parameters like width and L, now what I want to do is I want to vary the model parameters like threshold voltage and lambda of the MOSFET. We know that as threshold voltage increases, we need to give more VGS to turn on the MOSFET, right? So for more VGS, the device gets into turn on region. First, we'll see what is VTO. Yeah, here it's in the range of 0.42. So here it's given as 0.42. So we will take 0.2, zero point 0.4 and 1 volt and we'll check the analysis. We'll see ID versus VGS only. Okay, here I'll take varying VTO for user friendly. Now, yeah, I have did M1 I have defined fine. Instead of doing nested DC analysis, just I'll fix the VDS and I'll vary VGS because yeah, because just I want to see how the MOSFET is behaving by changing VGS. Like we want to see when device gets turned on if threshold voltage increases, right? Yeah, VGS. I'll take 0 to 5 in the steps of 1. Uh, Now here it's given as 0.42, right? So I'll take 0.2, 0.4 and 1. I'll see what happens. For each variable, what I want to take is 0.2, 0.4 and 1. And here it's given as alter M1. Here what we have to use is alter mod because now I am not altering the just parameter. I want to alter the model parameter whichever is given in the model file. So I have to write the syntax as alter mod. Yeah, which should be given to M1 and I want to vary what model parameter I want to vary VTO. So I'll be writing VTO equal to dollar variable. Yeah, it got varied. Yeah, now what I want to see is I want to plot ID versus VGS for every like 0 0.2, 0 0.4 and 1. All these things I want to plot in the same plot. So what I'll do is after performing this analysis varying the VTO, I'll plot things after completing the for loop. So after I'll do is plot. Here is the another way of plotting the things. Like I want to, if we want to plot more than one things, yeah. Here is the another way of plotting the things. Plot DC1 dot VDS hash branch -1. Yeah, we know that why we have -1 when we want to see current from VDS, we have discussed clearly in previous video. So this is the another way of plotting the things. DC1. What we are telling in this Ngspice is When in the iteration 1 means DC1, I want to plot VD, what is the current through VDS source with flipped sign. In a similar way, in the iteration 2, VDS branch -1. And in the similar way, third iteration. So DC3 dot VDS hash branch -1. Yeah, we have plotted. Yeah, fine. And we'll end this control block and we'll end this Ngspice code. And now I'll save this and I'll run. What error is showing? .vgs 025 unimplemented dot command. Okay. Yeah, it's giving. Yeah, here we will not use .dc. Yeah, .dc fine. So yeah, here we have used in the steps of one. Instead, for fine tuning, we'll use 1 milli. We should get now. Yeah, here we can see smooth curve. Here it's starting at 0.2, 0.4, and it's turning on at 1 volt. Yeah, we are satisfied for ID versus VGS we have plotted. Now, what I want to do is I want to plot ID versus VDS by varying lambda parameter. Here we can see level 1 model file. Here is the lambda parameter. It's given as 0.06. So we will take as 0.04, 0.4, and we will see and 2. And we'll see ID versus VDS. How transistor behaves, we will check. Yeah, dot DC VDS. Yeah, here it's a control block. Yeah, we will see how what should we do. Yeah, similarly, yeah, I want to alter mod M1 lambda parameter, right? So M1 lambda equal to dollar. First we have to define for each loop. For each, I'll take variable name as variable itself. Variable. I'll take 0.02 what it's given. 0.02, 2 and 4, and we'll see what it will happen. Variable. It's done right now. What I want to do is I want to plot on the same plot. So in the same plot for different lambda. So I'll plot after the control block. Sorry, after this for each loop. So run end, and after this I'll plot the things. Plot DC1 dot VDS hash branch for first iteration. This one for second iteration. And for third iteration. And after this, I'll end the control block. Dot end c done dot end. Yeah. Now we will run this and we'll check. Yeah, here. If I take more lambda, it's not behaving as trans MOSFET itself in the saturation region. So what we'll do is we'll try to decrease lambda value and we'll see 0.02. We'll take 0.04, and here somewhere around 0.5. We'll run. Yeah, here we can see that in saturation region, this red, blue, and yellow. Here, when lambda is increasing in linear region, it is not behaving. Sorry, in saturation region, the current is not same if lambda value is more. This we can get. Yeah, when lambda is 0.02 in saturation region, current is almost constant. But when we go to lambda equal to 0.5, around like that, the MOSFET is not behaving regularly how it should behave. Yeah, that's it for this video. In next video, we will discuss how to vary temperature and plot the things and. Also, we will see second order effect, which is bulk effect, which occurs in transistor MOSFETs. We will discuss that in next video. That's it for this lecture. Thank you.